All right, we are going to be looking at module number 7, which is CAM design, and we're going to go particularly into our learning plan. Our learning plan lets us know that we're going to be focusing on chapter 9 in our textbook, and the PowerPoint presentation that I have here is going to then help us focus on the sections that you'll be responsible for that'll lead into the homework assignment that you guys have. And sorry, it says homework assignment number 6. This is actually homework assignment number 7. All right, this is your 7th learning plan or module. So I'm just going to zoom out just a little bit here. So chapter 9. Now, our objectives here are really to look at CAMs and CAM followers. So we're going to start out by looking at different types of CAMs and CAMs followers. We're going to help you to understand the benefits of different CAM follower motion schemes, as well as be able to construct a displacement diagram, as well as the profile of a disc cam using a displacement diagram. Okay, so the last time that I taught this, we kind of broke this out into 2 parts. The first part was we kind of got through the cam displacement diagram stuff, and then we looked at that and kind of practiced looking at that, or practiced that, and then continued on to the profile of the actual cam. So I think that's probably how we're going to split it out this time as well. It kind of worked out really nice. So, introduction, this is going to start on page 223 in our book on, in chapter number 9. So basically a CAM is going to accept an input motion and is going to impart a resultant motion on a follower. Most often, well, and they're actually one of 2 ways. So either a CAM is going to move something in a linear fashion, a follower in a linear fashion, so that can be up, down, left, right, but it's going to be in and out linearly, or it can be something that's actually going to be pivoting and going to be following the profile of the CAM. So a very popular, application of a CAM is going to be looking at the engine valve train. So on page 223 in our book, that is the first illustration here in this chapter. So the CAM portion is going to be this part that is going in this case, it's showing that it's going to be going in a clockwise direction. The CAM has a lobe on it here. So as this rotates around and this lobe is in contact with this rocker arm, which is what we call the follower. So the CAM is actually going to be rotating around and it's going to be in contact with this follower. Now, since the follower is on the bottom, if there wasn't this valve stem with the spring underneath it, it would not be in contact with this because this would naturally want to pivot down out of the way. Okay, so this valve stem with the valve spring is actually keeping it up, and this part is in contact with that camshaft. Now, as that cam goes around and this lobe comes down, it is going to push this rocker arm straight down, which then is going to push the valve down. Okay. And then as this goes around, then it's going to allow it to go back up. That spring is going to keep it in contact with the profile of that cam. So as this comes around, it's going to go down, come back up, go down, come back up. So on each rotation of that cam, there's going to be portions where it's going to what we call rise or fall, and then parts to where it's going to actually dwell and stay in the same place. And that's all about timing. Okay, so in this chapter, we're going to be looking at not only this profile, designing this profile, this cam to impart a certain motion, but we're also going to be looking at what does that follower have to do? And we're going to be graphically showing its displacement on a diagram as well. So a cam can impart very distinct motion on followers, and it can do it in a pretty simplistic way. And it's all about timing. So as we look at how long maybe something has to rise or fall or go in or out, then we're also going to look at when do we want it to stay in those same places. So it's going to be used to obtain unusual or irregular motion, where even sometimes it's difficult to actually create it using linkages. CAMs are used in factory automation because they sequence displacements in a cost-effective manner. It's all about timing. Okay, so if we get those rotations to be at the right speed, and then they're timed out with whatever the operation needs to be, they're a really effective way that can mechanically actually keep things sunk together, if you would. Now, there are different types of CAMs. So as we turn the page, and we look at page 224, we're going to see a number of different types of cams here. Now, at the very top here, we've got what they just call plain disc cams. So where we see the place where we can put a shaft with a key, that's going to keep then this cam going at the same rotation as the shaft that would be in there. Here would be the place where we would put the shaft through, here, and then also here. And you'll notice that all of these have kind of those irregular shapes with lobes so that a follower can follow them as they go around one revolution. As we look down here, some more versions of cams. So a plate or a disc cam, like the ones that we see above. Notice that here's where our shaft is going to go through. It's keyed so that it stays, in the same rotational speed as the shaft. And then the follower itself up here, in this case, this is a pivoting follower with a roller on it, which stays in contact with the cam itself. So as this goes around and this lobe comes up, this is going to then pivot, around that fixed center in, as it follows. The next one that we have here is going to be a cylindrical cam. So notice that it's on the actual cylinder. There is a path that then the follower would be in, and then it's, as this rotates, this is going to allow the follower to go in and out, in this case, linearly. The next one that we have here is, this cam is not rotating about a center, but it's going to go back and forth, and then the follower is going to go up and down as it's in that groove. So a couple different ways that we can arrange cams and followers. Let's look at specific types of followers. So on the next column over here, focusing on followers, there's a couple different types. There's going to be an inline, offset, and a pivoting follower. So as we look here, an inline follower means that the center line of the follower and its motion is going to go right through the center of rotation of our actual cam, okay? When we're offset, what that means is, and you'll see that over here, now this is a little bit different type of head, but the center of and the motion of the follower is offset a distance from the rotation of the cam. So that's going to be an offset. The next one we have here is going to be a pivoting. So you'll notice here that it's on a fixed center. This follower, this roller in this case, is going to then pivot as this cam rotates around. Okay, this is also another type of a pivoting. So inline, offset, and pivoting are the main kind of categories or types. Then we start looking at the follower shape itself. So there's knife edge, roller, flat face, and spherical face. So those are examples here. So knife edge comes to a point, and so you have point contact along the edge of that cam. The roller, a lot of times this can be just a regular bearing that's going to be in contact with the outside, and it's going to roll along the face. The flat face here is going to then have a flat contact with it as it goes up and down. And then lastly, we have the spherical face. In all of them, there's a nice explanation in here of how all of the different types of followers, have advantages and disadvantages to each one of them. So the knife edge, it's really the most simple type, but because there's only point contact, it can actually dig into the surface, and then over time it can wear more easily. Another one is going to be the roller type. This one is, a very popular one. It can also be on an inline with a roller on the end of it, and that one provides the least amount of friction. So for higher speed applications, those are really nice. The flat face is very similar to the knife edge, except it has more lead in so that it stays in contact a little bit better and doesn't cause as much wear as soon, but there is more friction that builds up here. And then lastly, the spherical face is another one that if there is high pressure angles, which we'll learn about in a little bit, it can take them because there's that sphere on the front that can lead into the motion. So positives and negatives for each one of those types of follower shapes. So follower motion, okay, so there's translating followers. Those are going to be constrained to straight line motion. And then there's also swinging and pivoting, as we had seen earlier. So those are going to go back to that same illustration that we looked at. So translating or straight line is going to be anything that is going to be doing exactly that on the follower. And then pivoting is where it is pivoting around a fixed center. Those are the two different kind of main categories of followers. Now, follower position, as we saw earlier, is in line or it is offset. In line is going to be where the action of that follower linearly is going to be right in line, or we can extend that line right through the center of rotation of that cam. And then the same thing with the offset. There's actually a distance between. We looked at the different follower shapes. That knife edge follower is considered the simplest form. High contact stresses though, because everything comes through that one point. It wears rapidly, and it's not really used all that often unless it's quite low speed applications. The roller, this remains in constant contact with that cam. Most commonly used, as I said earlier, friction and contact stresses are minimized because of the rolling effect, but it can jam during steep displacements. And then we've got the flat face follower. This can take steep cam displacements without jamming because again, it's got that little bit of a lead in. It's used for quick motions as well as higher friction forces, and then deflections and misalignments can cause high stresses. And then the last one, the spherical faced, is going to be, it can be used on steep cam displacements without jamming because of that spherical end. The radius compensates for any deflection or misalignment, but the friction again is higher because you have, a surface that is rubbing over the surface of the cam. So, so depending on your application, each one of these can offer, like I said, positives or negatives. Prescribed follower motions. So we are going to be given, if you would, a task. So we're going to have in mind what we want our follower to do. So the amount of time required to complete a full cycle, so one revolution of our cam, is going to be shown as the summation of capital T sub I. And that's really then going to be each of the individual time increments that have to occur as we go around in one revolution of that cam. Then we're going to be asked to calculate the angular speed of a cam. So we're going to see this W come in, and that's simply going to be one revolution divided by the entire time needed to complete the cycle of the motion that we're looking at, okay? Because the motion that we're looking at has to be done in one revolution of that cam, all right? So our cam speed or angular velocity is going to be in RPMs. Then lastly, we can calculate the number of degrees or beta through which each one of the individual motions is going to be. And we'll see how we can take our rotational speed times the time and then multiply it by 360 degrees to see how many degrees beta is going to be for that part of the motion. So let's take a peek at example 9.1. Example 9.1. Now, it might be worth our while, before we get into the example, to just kind of write down an equation sheet, pulling these equations into one place. So I'm going to go back over here, and we are going to find the three equations. I think it's three. 1, 2, 3. Yeah, three equations here that we want to use for our problems coming up here. So I'm going to start an equations sheet. And we might add a couple more yet. So this one right here, this is our W of our cam. And this is the angular velocity of our cam, or angular speed. And this is going to be in degrees per time. Because a lot of times we want to know, all right, for that time segment, how many degrees of cam rotation is there actually going to be? So this would be the change in angle divided by the change in time to do that. So that'll be our first equation. Then we're going to turn the page, and our next one is going to be at the top of page 226. And this is going to be beta. Beta is going to say, oh, for a particular time of how long we want a motion to occur, what is the angle that we're actually going to use? So this is going to be our W of our cam multiplied by the time for which we need that motion to occur. Okay, so this is going to get us into like how many degrees of cam rotation are we going to be doing that? And then as we look here, to calculate the entire cam angular velocity, 1 revolution divided by the total amount of time for all of the individual motions that need to occur. So if I put over here, total time, it's going to be equal to T1 plus T2 plus T3, and then so on. However many individual motions have to occur in 1 revolution, okay? So this is, if you would, the full cycle, and these are the individual motions, okay? All right. So as we look at example 9.1, kind of start to bring some of these things together, okay? So in this case, we have a cam is to be placed or is to be used for a platform that is going to repeatedly lift boxes from a lower conveyor down here to an upper conveyor, okay? This machine is shown right down here. Plot a displacement diagram and determine the required speed of the cam when the follower motion sequence is as follows, all right? So down here is the motion. So there's going to be 5 steps in 1 revolution. The first step is for our follower to rise. So this is what we call a follower displacement diagram. So we want this follower to go up, all right? We want it to rise 2 inches, and we want it to take only 1.2 seconds total. Then it's going to dwell. That means it's going to stay in the same place for 0.3 seconds. Then it's going to fall 1 inch in 0.9 seconds, dwell for 0.6 seconds, and then it's going to fall the rest of the way because remember it rose 2 inches, so it has to fall 2 inches by the time it gets back around in 0.9 seconds, okay? So when we look at this, step number 1, the time associated with this would be T1. The next one for the dwell is going to be T2. The next one for the fall is going to be T3. Then we've got T4, and then lastly, T5, okay? Now, we need to determine what is the total time for this entire cycle to happen. So that's simply adding up each one of those T's. So, oh shoot, I had pieces of paper there. Okay. Put my equations on the back of something else that's written on. That's all right. It goes there. So, for this example, 9.1, we want to plot a displacement diagram. That'll make more sense in a little bit, but using some of those equations we were looking at to find the total cycle time, we need to add up each of those individual T's. So we're going to say, all right, the total cycle time is going to be equal to T1 plus T2 plus T3 plus T4 plus T5. So very simple. So now we're going to put our numbers in for each one. So 1.2 seconds plus 0.3 seconds, 0.9 seconds, 0.6 seconds, plus another 0.9 seconds. So our total time, we'll be adding all of those up. Now, I'm going to kind of peek here. Should be 3.9 seconds. Okay. So that's the time for 1 cycle. So this is 1 cycle, but it's also equal to 1 revolution on our cam. Okay. 1 revolution on our cam is going to be the cycle. So now the next thing we need to do is we need to determine the required speed of our cam. That's going to be our W, okay? So looking back over here, we can take our cam and it's going to be 1, I should have put 1 revolution divided by that total amount of time, okay? 1 revolution divided by that total number of time or total amount of time. So our W of our cam, why is this doing? I don't know. Stop. Close. Close. What is this doing? Why is this? There we go. I don't want to see the notifications off. I don't know why, I feel like I turn that off so often, but it always comes back on for me. I'm not sure why. So my W for my cam is going to be equal to 1 revolution divided by the total time we need for that cycle. So that's going to be the 3.9 seconds. So 1 revolution per 3.9 seconds, which is going to be equal to 0.2564 revolutions per second, right? Now, usually not a number that we like for the units, I should say, not the right units for an angular velocity. What units would we want instead? Yep, revs per minute. So RPM. So we're going to simply just do a conversion here, 60 seconds in 1 minute. Now our seconds cancel and our W of our cam is going to be, let's play that by 60, 15.38 RPMs. Okay. So this was one of our answers. This was one of our answers. So we'll put a box around that and we'll take a peek and we'll, yep, 15.38 RPMs. Good. Now, the next step that they have us do is they want us to determine how much cam rotation do we need for each one of these follower motions. Okay, so what we have so far is we know that the total time to do all 5 tasks, 5 steps in our motion is going to be 3.9 seconds, which is 1 revolution of our cam. Okay, and we know then to achieve that 1 revolution in 3.9 seconds, that means that our cam rotational speed needs to be 15.38 RPMs. Okay, 15.38 RPMs. But now, if I want to look at each one of those individual motions, instead of time, how many degrees is that going to be? Okay, I want to know how many degrees is it going to be for me to rise 2 inches in 1.2 seconds. Okay, how many degrees of rotation was that going to take? So if I look back at my equations, beta is going to be W of my cam times the time. Okay, my W of my cam times the time. So if I know my beta is equal to my W of my cam, oopsie, W of my cam times the time, right? And that's going to be of whichever section we want to look at. So we're going to have a beta 1 that coincides with that step number 1, a beta 2 for step number 2, and a beta 3, 4, and a 5. Okay. Now, as we look here, beta, we want to be in degrees, right? So if we multiply these two together, let's do it for beta 1. Beta 1 is going to be equal to W of our cam times, it's going to be T1. Okay. So if we look here, T1, if we look back up here, T1 is in seconds, right? T1 is in seconds. So we don't want to use RPMs. We want to use revolutions per second here for our W. So we want to use this 0.2564 revolutions per second. And we're going to multiply that by 1.2 seconds, which is the time it takes for that first step, 1.2 seconds. So cancel out the seconds, and we're going to have our beta in 0.2564 and 1.2 times. So that's going to be 20. No, I did that wrong. I was going to say it can't be 26. Yeah. 1.2 times 2, oopsie, 0.2564. I think I had 25.64 times 0.3077. Did you get? Yep. Okay. And that's going to be revolutions. All right. So it's like 1/3 of a revolution, but that's not degrees, right? How do I convert a revolution to degrees? No, not quite. How many degrees are in a revolution? 360. Exactly. So I'm going to go like this. I'm going to do my my conversion, 1 revolution goes on the bottom, 360 degrees goes on top. Okay, so my revolutions will cancel out. So my beta one is going to be 360 times that number. So that's going to be 110.76 degrees is equal to my beta one. I'll just kind of put a line underneath that one. Okay. So I would do this 4 more times for betas 2 through 5. So let's do another one together, and then I'll let you kind of finish them up and make sure that our numbers come out the same. So now we're going to do beta 2. Okay. W times our cam, a W of our cam, sorry, times our time 2. So we're going to take that 0.2564 revolutions per second, and we're going to multiply that by this time 0.3 seconds, right? 0.3 seconds. The seconds are going to cancel. Our beta 2 is going to be 0.0974 revolutions. Convert revolutions to degrees. 1 revolution, 360 degrees. Revolutions cancel. And we should get 35.08 degrees equals to beta 2. I'll put a box around that. So, okay. Did you guys get the same number? No. I don't know.
I think it was 0.3 seconds.
0.3. Oh, that's what you know what? I had seconds and then I canceled it. So I did 0.38. That's why. I'm so sorry.
No,
I read exactly what my handwriting looked like. So 0.2564 times 0.3. So 0.0769. Does that look better? 360 times. Yep, 27.69 degrees. And that matches. Now let's go ahead and you can do beta 3, beta 4, and beta 5. And just make sure that you end up with the correct values. All right. So it looks like mine all came out to match. If you continue to kind of look at the top of page 227, you'll see the rest of these come out. Now, it's important to always do a double check. I know they have it here, but each one of these betas 1 through 5, needs to add up to 360 degrees because it is 1 revolution of our cam. So it's always worth making sure that indeed they do. So 110.5, 27.6, just using their number, 82.9, 0.3, and 82.9 plus. Yeah, very close. I'm gonna check mine because I had mine a couple extra decimal places. 110.76, 27.69. Yeah, mine comes out to 360 or 359.89. I'm not sure if yours, if you held extra decimal places, it might vary just slightly. So it looks like those numbers are all good. Now, down below is a displacement diagram. Okay, so we haven't seen one of these yet. So it's going to kind of bring together what all of these different numbers mean. Now, displacement diagram, y-axis is going to be follower displacement. Okay, so it's what we want the follower to do. So linearly, we wanted this to rise 2 inches, dwell, stay in the same place for a while, come down 1 inch, dwell for a little while, kind of sit there, and then come down the last inch. And then I think, and that was it. And then start over again, go up, dwell, down, half, dwell, down, half, start back up. Okay, and so on. So the highest number along that y-axis is going to be the total amount of rise that we end up having on this cam. In this case, it's 2 inches. Okay. Then you're going to notice along the x-axis, this is going to be our timing. The length of this x-axis is going to be from 0 degrees to 360 degrees. Okay. Now, as far as plotting this out, you're going to be drawing displacement diagrams and cam profiles in CAD. Okay, so you have to kind of determine proportionately how is this going to work out. So as we look at, if you would, the rise of this cam being 2 inches, and if we kind of go along here, 1, 2, it's about 3 times longer on the X than it is on the Y. So if you would use, for instance, 6 inches along here, that means that you would go along here with the even increments, and it looks like they're using every 45 degrees, you would space those out evenly to be 360 for whatever length you choose. Okay. And then that would mean that you could then figure out you could figure out per inch how many degrees that would be, or how long a degree would be along that axis. Okay. So you've got degrees, and then you've got your betas. Okay. So our first one, beta 1, that was calculated to be 110 degrees. Okay, 110 degrees. So you'll notice that we go a little bit beyond the 90, and this is going to be the ending point then of that section, that first motion where we rise 2 inches. Okay, so from the bottom here, we're going to rotate that cam 110 degrees. And by the time we get to the top, we've risen 2 inches, and it has taken us 110.5 degrees, or our T1, which was 1.2 seconds. Okay. So notice that that's also part of this axis, is T1 and beta 1 go together. Then at the top here, now that we're at our rise, we're going to go in a straight line. This is the dwell section. Okay. So this is a dwell. So we remain at that same level for beta 2, which is time 2, which is 0.3 seconds. Once we've dwelled for 0.3 seconds, now we're going to start to go down. And our next one is going to be our beta 3, which is going to correspond to 0.9 seconds. Okay. And then we're going to fall 1 inch. So from here to here, this is our next height, if you would, our depth. that we're going to fall is going to be 1 inch. And then we're going to dwell again, stay in that same spot for a little bit, and that's 4.6 seconds. And then we're going to fall the rest of the way down to the beginning. Okay. And then right after that, as we rotate around, this 360 becomes our 0, and we're going to go back up 2 inches, dwell, go down 1, dwell, go down another 1, and then start back over, go back up 2, and so on for each rotation. Okay. So as we look at this again on the X and the Y axes, we would draw the height to scale, and then starting just as a guideline, try 3 times the length to see how that looks proportionally. If you need to make it a little bit longer, you can, but then you would take that overall length divided by 360 to know how many inches, if you would, like 1 degree would be, so that then you can multiply your beta by that many degrees, so you can mark off that length to scale so that you have the start and the stop for that amount of motion, that beta 1 or that T1. Does that make sense to everybody? Kind of thinking in terms of CAD. Okay.
Does the bottom always have to be degrees, or can it be in time, like the very bottom?
It really depends on what you're looking for. Most often we equate it to degrees. But I mean, it really, you can have the equivalent time on there as well. If for some reason you want to know both, you can put both of them on.
Okay. Well, I guess more for our homework, do you want degrees, or can we use, because then we potentially may not have to, because if we say we have, like, in this instance, like 3.9, you can figure out almost the same way,
Oh, right, exactly. You have your 3.9 and you could figure out, yeah, which those are. Honestly, it doesn't make a difference to me.
Okay.
But most often when we're talking about CAM, most often want to know what is the rotation, like what are the angles that it rotates through, so that if you end up changing how fast or slow that you actually rotate your CAM, then it becomes degrees is what you go off of. Does that make sense? They're both related, so it really doesn't matter which one, quite honestly. Okay, so that's a displacement diagram, and this is like the most complete, like labeled diagram that we have like in the chapter. So we'll go back and forth to this one to kind of use it as a guide. So that's our first example. Let's go back over here. So now let's look at follower motion schemes. We've briefly looked at or kind of introduced ourselves to that displacement diagram. Now the displacement diagram, as we saw, represents the motion desired in terms of distance on that vertical axis versus the angular displacement or time on that horizontal axis. Displacement diagrams give a graphical representation, so we could really kind of physically see what was going on. That is used then to generate the profile of the CAM. So you always have to start with, when you know the motion that you want and you know the time sequence that you're interested in, you start with creating that displacement diagram. The displacement diagram then is going to be used to create the CAM profiles. Okay, so we always start here. Now, for that purpose, they have to be drawn to scale. So if we've got a 2-inch rise, we're going to draw a 2-inch rise in CAD on that y-axis. Okay, and then when we do our x-axis, we want it spaced out far enough so that we can see those differences, and I'll show you where you can measure, but you want it to be proportional. So follower motion scheme, there's a wide variety of different motions that are available for moving that follower. Okay, the objective of each one of the schemes is to produce a movement that's smooth in and out of, like, the accelerations, or in and out of the motions that we're going to see. So slow moving CAMs, they have high accelerations are not a factor because of the fact that they are slow moving, and the displacement is going to, and really the follower is going to remain in contact while it's displaced, and everything will be okay. So when we have slow moving CAMs, accelerations are an issue. But when we have high speed applications where the CAM is rotating faster, then we do need to consider the implications of those accelerations, because what potentially could happen is that the displacement, that the follower could come out of contact with that CAM profile, and then now we don't have the motion that we want. Okay, so we have to then look to ways to minimize that vibration and the forces that we're going to see. Now in kinematics, we're not so worried about that. That's really a dynamics problem, but we have to kind of consider that as we decide on some of the things that we'll be doing. So we'll be talking about different schemes. So the nomenclature that we're going to have variables and such for displacement diagram calculations are going to be as follows. H is always going to be the total follower displacement. So we saw H on our displacement diagram for like the height, if you would, or the distance of a rise or a fall. Okay, so if we go back to that displacement diagram here, H1 referred to the height of the rise in step number 1. H3 is looking at the fall or the height for that fall in step number 3. And then H5 corresponds to the fall, the height of the fall in step number 5. Capital T is the total time period for a rise or a fall. Okay, so we saw that as those T1s, T2s, T3s. Lowercase time is going to be the rise or fall in interval that defines an instantaneous follower properties in seconds, and we'll see that a little bit later. Beta, I didn't show it as its Greek symbol, but beta is going to be that rotation angle of the cam during which you have a rise, fall, or a dwell being considered. Okay, so a beta, those beta 1s, 2s, 3s for each one of the sections of motion. Now theta is going to be the angle of rise or fall interval. So it's going to be the degrees. And then W is going to be the angular speed of our cam. So RPMs or degrees per second is going to be one that we use in and out of our equations. Now, capital R, I'm not sure why this book uses this variable, but for follower displacement, okay, is going to be R. And then V is going to be follower velocity, and then lowercase a is going to be follower acceleration. So the different motion schemes that we have. So what I'm going to do is I'm going to go underneath, starting on page 28. And I'm going to first kind of show you the different schemes. All right. And then we'll go back and we'll kind of discuss each one. So the schemes that we have, there's 4 main types. The first one is going to be constant velocity. Okay. The second one is going to be constant acceleration, harmonic motion, and then the fourth one is called cycloidal. Okay. Now, once we determine we're going to do our rises and our falls, now we need to determine how we're going to do them. And that's what these different motions are. So these are going to be our rises and our fall motion sequences. Now, as we look at constant velocity, this is the simplest one. Okay. And the shape of the curve, if you would, the displacement diagram would be literally a straight line. So on the top of page 29, here is the displacement diagram curved, really straight line, from where you would start to where you would end for a constant velocity motion sequence or a motion scheme. It would simply be a straight line. Now, this one is the least used, but only considered when we have very low speeds. Okay, very low speeds. Now, what ends up happening is because we say constant acceleration, or I'm sorry, constant velocity, right away you turn on and you're like full velocity right away in theory. We know that that can't actually happen, but it's like you're right away going as fast as you can at the speed that you're looking at, and you're going to stay at that speed until you get to your rise, and then you're going to stop. Okay, it's going to stop your velocity. Now, in that, because it's a constant velocity, really, that means that there's not an acceleration present. But when we're starting out so abruptly and stopping so abruptly, it's a very jerky motion. Okay, and the accelerations then are very high in and out of those constant velocities. So again, not used unless it's a very low speed application. Okay, now the constant velocity improves on this a little bit. So the constant velocity is going to be over here on page 230. So you'll notice the difference right away in the follower displacement. The follower displacement has a curve coming in and going out. So right away, you can imagine that this is going to be a smoother transition from when we start and stop a rise or a fall. Okay, so that is an improvement, but we still have the jerkiness of these accelerations. And they're not very smooth, and we can, if we're not in a lower speed application, we can lose contact with our follower and the cam profile. Okay. Now, constructing this, if this is one that's created, the construction is right down here. All right. And we won't be doing this construction for any of our homework, but it's here for reference. All right. So you would look at, for instance, this is your total height of your rise. You're starting at your start of the degrees of that particular period of time. And then what you do is you take half of it and you break it into 4 equal segments. And from the vertex A here, you are going to put the lines across. And then you're going to correspond to each one of the 4 evenly distributed or evenly spaced sections. And then you're going to do the very same thing on the other side of the curve, starting with point C here going out. And then through those points that occur on those divisions, you're then going to put a best fit spline through those. Okay, so you can imagine in AutoCAD how to do that. So that's constant acceleration. Now, the third one that we have is called harmonic motion. Okay. Harmonic is probably the most popular. This starts to be used for moderate speed applications. Okay, so here again, you're going to see our in and out follower curves, which is already a plus rather than being abrupt. You'll also notice that our velocity ramps up and then ramps back down. And our acceleration, yes, it starts out pretty fast. So it's pretty abrupt when it starts, but in the interim, it's a little bit more curved and then it stops suddenly as well. So our risk here is on the ins and the outs again with that acceleration of vibrations and then also non-contact with our followers. So again, moderate speed applications is what this is appropriate for. Now to construct this curve, okay, this one will be a homework assignment for you. And that is going to be shown at the top of page 232. So as we look here, this H is your total rise. Okay. So for instance, on that first example, that was our 2 inches. Okay. Now, as we look here, you're going to notice that that means that the total height here is 2 inches. So the radius of this curve of this half circle is going to be half of whatever your rise is, or 1 inch. Okay. So that's going to be 1 inch on either side here. And we create a half circle. Again, you can imagine in AutoCAD how to construct that. Once we have this in place, you'll notice that there's 1, 2, 3, 4, 5, 6 equal divisions. So if we take 180 degrees and we divide it by 6, you'll notice that's 30, 30, 30, 30, and 30, right? So we'll have 30-degree increments here. And then we're going to number from 0. Then we're going to go 1, 2, 3, 4, 5, 6. Okay. Now, along the x-axis, this is going to be our period in time, or our beta, or our degrees for how long that time sequence is going to be. All right. So in our case, for time 1, and we had that rise of 2 inches, it was 1.2 seconds, but it was 110.5 degrees, right, of cam rotation. So we find where that is, and then we divide that into however long this ends up being to scale into 6 even increments. Okay, starting with 0, then 1, and then all the way to 6. So then we put those lines going up, and what we do is from our half circle here, we're going to take number 1 and we're going to find the intersection with number 1 here vertically, number 2 horizontally, number 2 vertically, and so on and so on and so on. We find each one of those points, and then we're going to do a best fit spline through that curve to get that profile. Okay. That's harmonic motion. The third one, and another popular one, is called cycloidal motion. Now, cycloidal is really the best one of the 4 here in terms of when we start looking at higher speed applications and wanting to reduce that vibration or non-contact between the follower and the cam profile. So here you're going to notice we have our curves displacement wise going in and out. Okay, so that's what our curve is going to look like. So very similar to the other ones. They don't really look all that different. But now we can start to see a little bit of a curve and a ramp up to our maximum velocity and down. And then additionally, with our acceleration, it's no longer like this abrupt start and stop. Again, it's going to be a ramping up, ramping down. And so it's going to be the best one for high-speed applications. Now, to construct this, down at the bottom here is going to be the construction. So what we do is we find our total height of our rise. We determine what the total time frame is, the beta. We draw this to scale. Then from our sixth to our third and to our first, we're going to put a line straight through down to our 0. That's going to identify those 3 points. Okay. And then we're going to extend that down, and that's going to be where the center of our circle for our cycloid is going to be. Okay. Now around there, you're going to notice that we have 6 divisions again, but this time, because we're going around in a full circle, it's going to be 60 degrees between division. The first 2 here are going to be 0 and 6. Then we go to 1, 2, 3, 4, and 5. I'm going to zoom in a little bit here. Now, the diameter of this is going to be based on the radius is going to be equal to the height divided by 2 pi. So then the diameter will be 2 times that. Okay. Now, this center has to be along that line extended through 0, 3, and 6. Okay, so that comes straight down. Then what we're going to do is we'll have our diameter, and we're going to bring together 1 and 2 at the center here, and 4 and 5 at the center here, and 3, 0, and 6 are all at this center, which are on that center. So then what we're going to do is we're going to bring up from that midpoint a line parallel on either side through that point. Okay. And where it intersects is going to be where 1 and 2 points are. And then 4, 4, and 5, those are going to go up, 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 up to 4 and 5. And then now we're going to have that best fit spline through the points that we have along each one of those intersections. Okay. So that's going to be constructing the cycloidal. All right. Let's catch ourselves up on our follower schemes. We talked about harmonic, cycloidal, and then we've got a couple examples. Let's do these together. So this is example 9.2 and 9.3. All right. So we want to follow the steps just 1 through 3. So we're going to be doing this in a graphical mode, and we're going to be plotting our displacement diagram using CAD construction. So if we go underneath here, we're going to first look at example 9.2. Example 9.2. So we've got a cam. It is to be designed for an automated part loader, as we see over here, as shown. Using the motion equations, construct a chart that tabulates the follower displacement versus time. So we're going to create that displacement diagram. We also want to plot this data when the prescribed motion for the application is as follows. So number 1, it says we want to rise 50 millimeters in 1.5 seconds using constant velocity motion scheme. Okay. Then we want to return in 2 seconds using cycloidal. Then we're going to dwell for 0.75 seconds, and then we're going to repeat. So in this case, we have 1, 2, 3 steps of motion corresponding to the time that we have here. So our 1.5 seconds is T1, our 2 seconds is T2, and our 0.75 seconds is T3. So that means adding up those 3 is going to give us our full cycle. So let's start an example sheet here. So example 9.2. So first of all, our summation of our TIs, or our total cycle time, is gonna be T1 plus T2 plus T3. Okay, so that's gonna be 1.5 seconds plus 2 seconds, I like writing out seconds, so it looks more like seconds, plus 0.75 seconds. So our total cycle time, we'll be adding those three together. So I think I get 4.25 seconds. Is that what you guys got? Looks like that's correct. Okay. Now, the next thing we always want to do is we wanted to know what is the rotational speed of our cam? Okay, what is the rotational speed of our cam? So that's step number one. Step number two. So our W of our cam is going to be equal to 1 revolution divided by that total cycle time. Okay, so we know that 1 revolution divided by 4.25 seconds. Okay. And I get 0.2353, and that's going to be revolutions per second, right? Now, most often we want this in RPMs, so we're going to say W of our cam is going to be equal to 0.2353, sorry, revolutions per second, and we just want to convert that to revolutions per minute. So we multiply 60 on top, and we will get 14.12 RPMs. And that's equal to our W over cam. Now, the next thing we can do is we can determine what are the cam rotation angles for each one of those motion sequences. So we need a beta 1, a beta 2, and a beta 3. Okay. So step number 3 is going to be kind of converting those times into angles. So we know that beta 1 is going to be equal to our W of our cam times our time 1. So that's going to be 0.2353 revolutions per second times 1.5 seconds, right? Seconds cancel. And our beta 1 is going to be in revolutions, 0.2353, 1.5 times. So this is going to be 0.353 revolutions. And then we're going to convert that 1 revolution, 360 degrees. So multiply by 360, and we get beta 1 equal to 127 degrees. Okay, so that'll be our first motion sequence for that many degrees of cam rotation. Then we're going to do that very same thing for beta 2. So W of our cam times T2, so 0.2353 revolutions per second, this time times 2 seconds. Seconds cancel, and our beta 2 0.4706 revolutions. Convert that to degrees. So we get 169.4 degrees is equal to beta 2. And then our last one, beta 3, same thing. W of our cam times T3, 0.2353 revolutions per second times 0.75 seconds this time. So our beta 3 0.1765 revolutions, revolutions. And then convert revolutions to degrees. So that comes out to be 63.53 degrees is equal to our beta 3. So now we should be able to add up these three to get 360, or very close to that. 27, 169.4 plus, and then 63.53. Pretty close, so 359.93 degrees. If you add up my numbers that I rounded, is anybody closer to that or right on? Pretty close. Okay, questions so far? All right, now we're ready to plot our diagram. Okay, plot our diagram. So now what they did over here is they used Excel, okay, to get all of their times, cam angle, and their follower displacement, okay, and then used Excel to plot the curve, okay. I mean, you could do that. You could do that if you wanted to, but we can also do it manually using AutoCAD relatively simply, okay? So, so we will notice that on the following page here is where they do that construction for creating that displacement diagram manually, okay? And that's what we're gonna do in AutoCAD. So I'm going to open up AutoCAD and kind of walk you through the process of drawing this to scale so that you have an idea of what's expected for the problems that you'll be working on. And I actually want to open up a template, and we are in millimeters, right? So I'm going to do a metric template. All right, so now again, it's really important that we draw this to scale because we are going to be using the distances that we get to create then our cam profile to scale. So, so as we look here, you'll notice that we're going to need to make an X and a Y axis. So I'm going to start with a line, and I want to put my ortho on. I'm just going to start here, and my follower displacement vertically is going to be a maximum of 50. So I'm just going to simply draw that 50 millimeters long. Now, a place to start, a good place to start, as we look at the 50 here, as I said earlier, if we look underneath, you'll notice that you have 50 on that axis. And if you could kind of go 1, 2, 3, about 3 times that length is going to be a good guidance or a good place to start for the length of your x-axis. So that's what I'm going to do. Since we had 50 along the y, I'm going to draw a line then, starting here horizontally, going 150 millimeters long. Okay. All right. Now what I want to do is I want to find each one of my divisions along that X and Y axis. Okay. Or I should say along the X axis. So if I know that 150 millimeters is 360 degrees, then I need to find out how long is 127. Okay. So to do that, I can simply set up a ratio, right? Now again, you don't have to use the same numbers that I'm using here, but like I said, it kind of 3 times the length is a good number. So number 4 here, well, I probably should say that the next part here is example 9.3, because this is going to be drawing our diagram. So step number 4 in this problem is really going to be trying to figure out how long is 110, I'm sorry, not 110, 127 degrees along our axis. So if we know that 150 millimeters is equal to 360 degrees, then we want to know how many, we'll call this x1, what distance is 127 degrees, right? So we simply multiply 127 by 150 and divide by 360. So do you get x1 equal to 52.9 millimeters. Is that what you got? So 127, 150 times 360 divide, yeah, 52.92 millimeters. So that means if I go back to AutoCAD here, I'm gonna offset from what would be my 0 degrees here, 52.92 millimeters from here to here, okay? So that's gonna be my first beta 1. Does that make sense? Okay. Then my next one is going to be 169.4 degrees. So from here, I want to know, all right, how much further is my next one? So going back underneath here, for 169.4, we'll do that very same thing. We know that 150 millimeters is over 360 degrees. We're going to set that equal to, we'll call this x2, and that needs to be 169.4 degrees. So we'll multiply 169.4 degrees times 150, divide by 360. And I get x2 equals 70.58 degrees. You guys, or no, I'm sorry, millimeters. Okay, because that's a distance. My degrees are going to cancel top to bottom. Did you guys get that same thing? Okay, so now I'm going to go back to AutoCAD and I'm going to offset one more time. And this time it's going to be 70.58 from here to there. And then to the very end here is my last chunk, right? Because this is 360 degrees at the very end. So, so I don't need to measure that one out. Okay. All right. So now if we know that, go back to the motion. We want 50 millimeters. We want to rise 50 millimeters in that first 1.5 seconds or 127 degrees. Okay. And this needs to be constant velocity motion scheme. Now, we aren't going to be using this one for our homework, but we can simply go back and we're going to find how to construct constant velocity. It's really easy. That's why we're not doing it for our homework. It's just a straight line from 0 to our endpoint. That's it for the height of 50 millimeters. So for that first section, okay, I'm going to go back to AutoCAD. For that first section, we're simply going to draw a line from 0 to the top up here. And that is our first constant velocity to that. Then what we're going to do is, if we go back to our example, we're going to return, meaning we're going to follow the full 50 millimeters in 2 seconds, but now we're going to use cycloidal motion, okay, on that backside. So now we have to construct it. And we're going to look at cycloidal motion. Construction is right down here at the bottom of page 233. Okay, at the bottom of page 233. So let's kind of sketch out what we need to do here. All right, so you'll notice that we need to draw a circle, and that circle's radius is going to be equal to height divided by 2 times pi. Okay, so I'm going to say r is equal to height divided by 2 pi. So my height of my rise is 50 millimeters divided by 2 pi. So 50 divided by 2 divided by pi. My radius is 7.958 millimeters. So that means my diameter is double that, right? So I'm going to go back to AutoCAD. Okay. And I know that my motion is going to start up at this point. Okay. And I'm going to change this to a dotted line. So I'm going to draw my line from the top of this. I'm going to turn off ortho and go to the bottom down here. Okay. And that, oopsie, that did not go to the end point. Hold on. Line, endpoint, endpoint. Okay. And then what I'm going to do is I'm just going to draw a line down here to extend this line too, just so that it extends beyond. Okay, and then along this line is where I'm gonna draw that radius of a circle. So I'm gonna draw a circle, and I'm just gonna go shift nearest circle, shift nearest, like right about here. And that radius of that circle needs to be 7.958. There we go. Okay. All right. Now I'm going to draw a line from the quadrant across. Quadrant, there it is. From this quadrant to that quadrant. Okay. And then I'm going to trim this back here and here. Because I don't know that that is degrees. Now what I want to do is I want to do my even 6 increments around here. So I need to have lines that are every 60 degrees. So I'm going to do a rotate of this, enter. My base point is going to be the center. I am going to do a copy because I want to leave behind a copy, and I want to say 60 degrees. Okay, so that's 1. And then I can mirror this from here to there. Okay, so there it is. Now I'm going to extend this back to my center. I just didn't want it to interfere. And I think I'm going to change, I'll change these to blue. So I'll change this just so that they're a different color than that side. Oopsie. I'll change them to blue. Okay. Now, as we rotate around here, we know that we are going to be connecting these top 2 and the bottom 2. Okay. And we're going to need to draw a vertical line going through here and a vertical going down there. Now, as we look here, we're going to draw, I'm going to copy, I'm going to offset this line so that it's going to go through that center and through that center. Okay, so you kind of see my construction here so far. All right, and if you take a peek at page 233, this is consistent. I haven't put my labels on yet, but this will be the same thing. Okay, now as I correspond here, I am going to now, since I have 6 divisions around my circle, I need to take and divide this length right here into 6 equal segments. Okay, 6 equal segments. So I need to measure that again. I think my paper fell down. And the measurement of that distance was 70.58 millimeters, right? So to get the even increments, I would simply divide that by 6, right? Yeah, so each increment should be 11.76. So I'm going to do an offset of 11.7633. And I should be able to get 1, 2, 3, 4, 5, and then my 6th division. Okay. Okay, does that make sense to everybody so far? All right. So now we're going to look, when we're coming back down on the fall, this is the opposite of. So this, if we go, is going to be my 0, my 1, 2, 3, 4, 5, and 6. Okay. So that means that I'm going to put points down. I do the points here. Hold on. Where's my point? I'm going to do it on the draw menu. Draw. Do I see point? There it is. There, a single point, right? So my first single point is going to be at my number 6, which is at the very end, right there. My next point, I'm just gonna hit enter to go back into that, is gonna be at my third one right here. Okay, and my sixth point is gonna be down here at this intersection, okay? Now, how do I do that where I show my points? Well, I'm okay. I have the points there. They'll find them. They're nodes. And then now what I'm gonna do is I'm gonna place points. So for this one going along here, this is gonna be my 4 and my 5. So that's gonna be this point and this point. So I am going to do that same thing, draw point, single point, and it's gonna be at this intersection. And then my next one, I can hit enter to go right back in, is gonna be here. Whoopsie, there. Then my next one is going to be as I look at my 1 and my 2, they cross here and here. So I'm going to do that point again, single point, and it's going to be at this intersection and at this intersection. Enter that intersection. So there are points there. All right. So now all I have to do is I am going to do a best fit spline. So we'll stick with the blue on the border just for a different. And right here, you're going to notice I have a spline fit. It's all the way over to the left. Okay. And now what I'm going to do is I'm going to grab these points. So I'm going to start up at my 6. I'm going to go to my 5. I'm going to go to my 4, go through the center of my 3, then my 2, 1, and then my 0. And then when I get to the bottom here, you just want to kind of go further out and then hit enter. Okay. If you hit escape, like we do sometimes to end a command, it won't register. So now I'm going to quickly hide these guys. And now you'll see here's the construction of my cycloidal line as it falls down to the bottom there. Okay. And then this last portion right here is going to be the dwell. Okay. So I rose, I should really change this to my border. That one. I rose, that's my travel. I rose 50 millimeters using constant velocity, and then I fell using cycloidal to the bottom here. And now I dwell out to the end of my 360 degrees. Okay. Now, to finish this out, and I just don't want to take the time just because it takes a while, as you know, you would then add the labels to the X and Y axes. Now, I will leave it up to you. If you want to do the time across that Y axis, or if you want to do the betas in degrees, that's totally fine. But you kind of want to show where the start and end of your first time frame of your motion, the second time frame of your motion, and then in this case would be the third. If you have more than that, then you would want to show those different zones, if you would, with the construction. Okay. So if I turn this back on, that would be that. Okay.
You want us to turn it, so, well, a few things.
Mhm.
One, do you want us to label like the circle on the bottom?
You don't have to label it. It's going to get so crowded with like letters and numbers and stuff like that. The axes, yes, but these you don't have to.
Okay.
Does that
I
make
was gonna
sense?
Say too,
Yeah.
You want those in there to show that we did it, or did you?
I do like to see them. So, like I said, I have mine on a different line, type here. So yeah, I do like to see it because then I can see that you know, what the construction was, whether it was harmonic or cycloidal. Yeah. Yeah, please do. But the labeling as far as around here, you don't need to do, but like we figured out, you know, what that radius would be. I do want to see that calculation, like on the handwritten. Okay.
Do you want the lines on there with the circle?
This one right here.
Yeah.
Yes. Yeah. That one I do want to see because that lets me know that you divided it into the 6 equal segments and where they came together. Which one?
Anyway.
These hidden lines. Yeah, I do like to see those. Yeah. And if you want to use different colors or line weights, that's totally fine. Mhm. So what you want to kind of duplicate, if you would, is we go underneath and we look at this example, you'll notice how they showed this. Okay, so this is what, I would want to see. The vertical and the horizontal axes laid out. You would show your circle here, but you don't have to put all the labels on it for the sizes, but then just kind of those construction lines going up. And then showing kind of, those different zones, if you would. In this case, they did the angles. If you wanted to do the time, you could in seconds, but this would be a good illustration of what you would want to show minimally. Okay. So that is how you create some examples for the displacement diagram. So let's look at your homework assignment associated with this part of it. Okay. So, I'm going to go to our module number 7, our assignment number 7, and the first 2 homework problems are going to be associated with displacement diagrams. So if we look at 9.7 and 9.9, okay. These start on page 254, okay? And these are the graphical displacement diagrams. So 9.7 says we have a cam drive is used for a mechanism that tests the durability of an oven door. The cam follower must rise upward or outward 2 inches with harmonic motion in 1 second, dwell for a half a second, fall 2 inches in 1 second again. Okay, now the nice thing about this one is there's a mirror here. Okay, on one side, it's when the motion is the same rise or fall and the same amount of time. So in this case, you're going to see it's going to rise 2 inches, it's going to fall 2 inches, and it's the same amount of time. If that time is different, then it's going to be distributed over a longer or smaller line, and it's not a mirror. So this one actually can be a mirror for that other side. And then it's going to dwell for the last second, and then it's going to repeat the sequence. So you want to determine the required speed of the cam. That's our W of our cam. And then graphically plot the follower displacement diagram. Both sides are harmonic. So the harmonic motion construction is going to be found on page 232. Okay, 232. So since this rises 2 inches, then this radius is a radius of 1 inch for a total of 2, divided into 6 equal segments. Then this length is going to be 6 equal segments for whatever that motion is for that amount of time. In this case, it was 1 second, right? And then you're going to come over with each one of those lines for the intersections of the spline fit to go through. Okay. So harmonic for both the rise and the fall on that one. And then number 9.9. So a similar type of a problem, but this time you're doing cycloidal motion. Okay. So here the cam must move outward 1 inch cycloidal motion in a second and a half, fall 1 inch in 1 second. So this one is not a mirror image, even though the rise and the fall distance are the same, the time span over it isn't. Okay. So this one's a little bit shorter. And then dwell for a half second and then repeat. Determine the speed of the cam and then graphically plot that follower displacement diagram using the cycloidal this time on both sides. Okay. So, so that's where I'm going to stop. Does anybody have any questions as you're just kind of looking at the assignment at this time? Okay. All right. You might, as you start working on things. So the next time we get together, the first thing I'm going to ask is what questions do we have on displacement diagrams? And I'll take any questions or go over anything that you might have. And then once we've exhausted those, then we'll move into finishing up the chapter and looking at creating then the CAM profiles, okay, using these displacement diagrams. All right, so that's what I had to cover this evening. So I am going to, if there aren't any questions, I'm going to stop our recording.